No, and this. So we want to use technology to see if we can build a conclusion off of what raising to a fraction power does. So right there, what we've got is 9 raised to the 1/2 power. Okay, I have to have parentheses here because if I put 9, and that might have been the issue, Caitlin, when we did that, and I got 4.5 back because I didn't put parentheses around the 1/2. So if I go 9 raised to the 1 divided by 2 and no parentheses, it's going to take 9 raised to the first power, which would be 9, and then divided by 2, which would be 4.5, right? We don't want 4.5 as a result here. So we got to put parentheses around the 1/2 because we want 9 raised to the 1/2 power. Okay? Hit enter. What's it give you? Gives you 3. What's another way that you know how to get 3 from 9? Okay, you divide it, maybe dividing 9 by 3, that would work. Let me do this. Let's go, what's that thing? Square root, okay? So if I take 9 and take the square root, I also get 3. Take 16. 16, raise it to the 1/2 power again. So I'm using, where'd Garrett go? Okay. I'm using 1 divided by 2. You can use 0.5 if you want, okay? So if you want to use 0.5, that's fine. But there will be times where it's not 1 divided by 2, maybe it's 1 divided by 3. And then I don't want to use like 0.33333. I would want the fraction 1/3.
That's how you do it, right? I just want to make sure
Yep, that'll work. Yep. So if I do that, so what's that give you? 4. How can I get 4 from 16 alternatively? Square root. Okay? Let's do this. Let's use a kind of an odd, bizarre number here. Let's go 17. 17 raised to the 1/2 power. 17 raised to the 1/2 power. It's kind of weird though, right? 4, 1, 2, 3. That's weird. First 4 numbers. So let's take that real quick. Take that number. Type it in once. So you go 4.123105626, and then multiply by itself against the 4.1. 4.123105626. Okay. Hit enter. What's it give you? 16. Or sorry, 17. Sorry. So what is raising something to the 1/2 power equivalent to doing? Square rooting. Okay. By definition, we just found that this number here multiplied by itself gives me 17. So this number here must be the square root of 17. Okay. So we have a rule here that says if we can use any variable we want to, I'll use n. So if n raised to the 1/2 power, that is equal to, you don't even have to write the word if you don't want to. So n to the 1/2 power is equal to the square root of n to the first. Okay. N raised to the 1/2 power is equal to the square root of n to the first. Those are equivalent. So 9 raised to the 1/2, we just went through 9 raised to the 1/2 power was equal to the square root of 9 to the first. Does that make sense? We had 16 raised to the 1/2 power. That was equal to the square root of 16 to the first. Okay. What I want to see here, what I want to demonstrate, is that this denominator of 2 in my exponent matches to that index on my radical, right? This 2 right here matches to that index. This 2 right here matches to that index. Is it okay? This 1 right there matches to the exponent right there. What? So an alternative way of writing a radical. If I take a radical and I want to rewrite it a different way to maybe do algebra a little bit more conveniently, I can write it as what we call a rational exponent. Rational means ratio, right? Okay, 1 to 2 is a ratio. So that's a rational exponent. It's a fraction exponent. Let's do this real quick. Take your calculator and let's go. Now this is where typing it n as a decimal isn't going to be useful because I want to do cube roots here. So take 8 and raise it to the 1 divided by 3. Make sure I put parentheses around the 1/3. Gives us 2, right? Okay. Let's do 27 raised to the 1/3. Gives me 3. Okay. Let's go 64 raised to the 1/3. Oh. Okay. So let's think about this. What's 4 times 4 times 4? 64, right? So take this number 4, multiply by itself 3 times, it gives me 64. What's 3 times 3 times 3? 27, right? What's 2 times 2 times 2? 8. So by raising to the 1/3, we are seeing that we are getting, she was wrong too. I named her Noah because she's usually wrong. I'm kidding, Noah. So what we're seeing here when it's into the, and this is how a lot of rules are developed. It's called a proof by induction. Now there's a lot of like syntax and procedural stuff that you have to do in a proof by induction. But basically it starts off with, if I take 8 and raise it to the 1/3 and I got that to be 2, and I got, what do we say the other one was? We went 27 to the 1/3, and that gave me 2, or not 2, sorry, 3, messing up. And then I went 64 raised to 1/3, and it gave me 4. Basically, what we determine is, okay, well, this gave me the cube root of 8. So 8 to the 1/3 must be the same thing as the cube root. Oh, sorry. Yeah. So we can basically say, well, I know 8 to the 1/3 gave me 2, but the cube root of 8 also gives me 2. 27 to the 1/3 gave me 3, but we also know that the cube root of 27 gives me 3 as well. And the same thing can happen here with the 64. So what does that mean? What it shows us is when I go 1/3, that denominator right there becomes that index, right? That denominator right there became that index. That denominator there became that index. The numerators, they all became, tablet died. The numerators, they all became the exponents of the radicand, correct? Is that the same pattern that happened over here? Well, careful. We extend it a little bit further. so those numerators became what's underneath the radical. So now let's do this. Let's go. Try to figure out an example here that's going to be easy to realize. You got to think about what exponents do for us. Okay, exponents show me repetitive multiplication, correct? So if I had 16 squared, that would mean 16 times 16, right? If I had 16 to the third, I have 16 times 16 times 16. But here I have 16 to the 1.5, essentially. Okay? Well, that's not multiplying 16 by itself a complete 2 times. Does that make sense? Okay, it's multiplying itself by itself 1.5 times. So we really have to think about what does that mean to us. Well, if we type in 16 raised to the 3 halves, 16 raised to the 3 over 2, okay, that gives us 64 in this case, right? Okay, so let's do this real quick. Let's kind of follow the same pattern that happened with these numbers up here. Now, the numerators are a little bit different, but where did this denominator go, these blue numbers, where did it go when I wrote this as a radical? It went on the index, right? It went on the outside, correct? So when I see this denominator of 2 right there, I'm going to put it right there. So I'm going to take the square root, okay? Now when I go 16, okay, this exponent kept going with the radical, or the radicand on the inside, correct? So up here it was n to the first, here was 9 to the first, here was 16 to the first. What am I going to put in here? Using the same pattern. 16 to the third. Okay? Now, let's kind of see what happens here. Let's take 16 to the third and see what that gives us. So let's go 16 to the third power gives us 4096. So I'm asking now, what is the square root of 4096? Okay. Well, it is 64, but let's go through our kind of process that we've gone through in the past. We would know we go 2 in 2000, 48 here. Then we would go, let's do this easier. So it's 10 and 24, 2 and 10, 24. That's up 4. This would be 2 and 5, 12, 2 and 256, 2 and 128. So remember doing this, right? 2 and then what's that going to be? 60? No, sorry, 70. It's 128. Yeah, 64. I don't know why I couldn't do that math. 2 and 32. 2 and 16. So there's a lot of 2's here, right? 2 and 8. 2 and 4. 2 and 2, correct? All right, so let's group these. So there's one group of 2's, 2 groups of 2's, 3 groups of 2's, 4 groups of 2's, 5 groups of 2's, 6 groups of 2's, right? So those all come out. So it'd be 2 times 2 times 2 times 2 times 2 times 2, or 6 of them, right? What's 2 to the 6 the same as? 64, right? Isn't that what we saw with our calculator when we typed in 16 raised to the 3 halves, right? So what I'm trying to demonstrate here is if we have, I'm just going to use n, and I'm going to raise it to the a over b, okay? So some number raised to the a divided by b. What that turns into is going to be the root that we're going to take is whatever that denominator was. So some of those we saw that the denominator was 2, so we're taking the square root. If the denominator is 3, we'll be taking the cube root. If the denominator is 4, we're taking the fourth root, right? Okay? And then the A is the exponent that goes on the inside. Okay? So earlier I said like n raised to the 1/2 was the same thing as the square root of n to the first. Sometimes you'll see like n raised to the 1/b is equal to the bth root of n to the first. Okay? But those two things right there are just special cases of that first rule that I gave you, because they're just special cases in which a in that one that says n to the 1/2, there a would be 1 and b would be 2. Okay, and that bottom one, it's a special case where a would be 1 and then b would be anything. Okay, does that kind of make sense? And this is a two-way street, meaning that you can go from, it's the equation, so you can go from writing your exponents as fractions to writing it then as a radical. So let's do a little practice. Let's say I gave you like x to the 7/5. How can you rewrite that as a radical? Yep, there you go. Okay. And they're going to ask you to go back and forth. And here's the reason why we like this. Let's say that I gave you, well, let's do this example first, and then we'll go into maybe the purpose of this. So let's go, let's say we had the 8th root of x to the 3rd. How can I rewrite that then as a fractional exponent, or rational exponent? 3 divided by 8 as my exponent. Okay, so here's why we like this. Let's say that I asked you to take the square root of x cubed and multiply that by maybe the cube root of x to the 5th. That's kind of hard to do. Okay, all the rules we've talked about so far with radicals and multiplying is that the radicands had to be the same base. Okay, and basically what we're talking about as well was that the radicals, the roots, had to be the same. I had a square root and square root, or a cube root and a cube root. Here I don't have that. They're different. Here's a cube root and a square root. But what we can do is say that this one, how would you rewrite this one? How would you rewrite that one as x to the what? 3/2. Times then, this one you'd write as x to the 5/3. Okay? Now we can do that multiplication, because when we multiply like bases, does anybody remember what we do with the exponents? You add them. So I have x to the 3/2 plus 5/3. Okay? Now that's a nasty set of numbers as fractions to add. What do I need if I want to add fractions? Common denominator. What's the common denominator going to be here? It's the smallest, and that doesn't have to be the smallest, but usually that's the best for us. So we're going to say the smallest number that the denominators can both go to through multiplication. So 6, right? The fastest way to find a common denominator is just take your denominators and multiply them together. So if that's going to become a 6, I need to multiply it by 3, right? So I need to multiply the top by 3 as well. So 9/6 is the same thing as 3/2. Okay? What do I need to multiply this one by? 2. So it's going to give me 10/6, right? So now I can add those. What's 9/6 plus 10/6? 19/6. Okay? Now, so that is what these two things multiply together to give me. Let's change this back into a radical. I'm going to turn it into a radical. I got to have the x there. What number goes here? The 6. And what number goes here? 19. Okay. Does that kind of make sense? Okay, so let's go to Desmos real quick and see if we can make sense of this with our technology, of what we just did. We said we were going to take the square root of x cubed and multiply that by the cube root of x to the fifth, right? Doesn't give me anything back. But we went through all this work, okay? And we say that that is equivalent to this, which was eventually then equivalent to this. So I'm going to type in the sixth root of x to the 19th, okay? Now all I have to do is tell x to be a number. Let's say x is 12. Does it give me the same result? If x is 115, it gives me the same result, correct? Okay? So what this allows us to do, and this is mathematics in general. So this is what mathematics is in general, is it's a set of rules and procedures, relationships that we are able to use to allow calculations to be done easier. What I've got a box up around there, you can't do. Okay? I don't know how you would go from just using the numbers that are up here with these numbers to get the 6 and the 19 from that. Okay? But these rules in with radicals allows you to get there. There is a Math Excel assignment that is open over this stuff. I was just kidding.
I know.
Okay, you got kind of quiet. On the quiz tomorrow? I don't know.